Hi, my name is Talia. I'm a high school senior and I love teaching others about chemistry and math. This YouTube channel is an extra resource for anyone who may be needing some extra help in their chemistry classes. This week, I'm going to be wrapping up my unit on stoichiometry and talking about limiting and excess reactants. So I hope that if you need some help with that topic, you'll keep on watching. Without further ado, let's get started. Okay, so this week I'm going to be talking about limiting and excess reactants. Limiting and excess reactants basically show that when you are creating a reaction, sometimes you might put too much of one reactant into the reaction, and it would be more than the amount that would be required by the law of conservation of mass. So you'll notice a common trend that with the first video of this unit, I explained stoichiometry in a perfect world, and my previous video in percent yield, I explained one kind of human error when a different amount of the product is produced than would be calculated. And in this video, I'm going to explain another possible error, that too much of one reactant might be added, and that causes you to have limiting and excess reactants. When doing stoichiometry and you're given the mass of two reactants, you need to calculate which one is the limiting reactant and which one is the excess reactant, because that will give you, each reactant will give you different answers, and you want to make sure you're using the correct one. So the law of conservation of mass kind of takes a detour when you're given the mass of two reactants and you have a limiting and excess reactant problem, because not all of the excess reactant will be used in the reaction. You are going to have more reactant mass than product mass in the beginning of the problem. However, once you use the limiting reactant to calculate the mass of the products, if you end up needing to find the mass of the reactant that is actually used, and your numbers will be compatible with the law of conservation of mass once again. So when you're given the mass or moles of both reactants, you determine the moles of both of them and divide by the coefficients in front of the compound. And this kind of evens the playing field with both of the reactants, because you can use the divided number of moles to figure out which is the limiting and excess. Whichever moles are larger represent the excess reactant, and the smaller number of moles represents the limiting reactant. So once you figure out which reactant is limiting and which one is excess, you are only going to use the limiting reactant for all of your future calculations. And that includes when you are calculating the mass of the excess reactant used, if your problem asks for that. So when you are asked to calculate that, you are going to use the moles of your limiting reactant and basically do stoichiometry, calculate the mass of your excess reactant that would be used, and then just subtract that from the given mass, and you will get the amount remaining. So we also have to make sure that when we divide the moles of both reactants by their coefficients, whichever one you end up concluding is your limiting reactant, that you don't use that divided number for future calculation. For instance, if you divide the moles of sodium by 2 and you figure out that that is the limiting reactant, you want to use the original number of moles to figure out the mass of the products. You do not want to use the divided number, because that is not the actual number of moles in the reaction. So let's now practice the limiting and excess situation. We're going to do one practice problem, and then I'm going to incorporate everything we've learned so far in stoichiometry in one large problem. So we have 4.95 grams of ethylene is combusted with 3.25 grams of oxygen. So first we're going to write a balanced chemical equation. So we know this is a combustion reaction, which means we are going to have a hydrocarbon plus oxygen yield H2O and CO2. So let's write our hydrocarbon, C2H4 plus O2, and then that yields CO2 and H2O. Now, I like to balance in the order of carbon, hydrogen, oxygen, so I'm going to place a 2 in front of 2 CO2 and a 2 in front of 2 H2O. So now we have 2 carbons and 4 hydrogens, and now we have 6 oxygens. So I'm going to put a 3 in front of the O2. So now we have done this first step. Now we have to calculate what the limiting reactant is. So I'm going to draw my table. Again, you do not have to do this table. I just think it keeps everything really nice and organized. So I'm given 4.95 grams of C2H4 and 3.25 grams O2. Let's first calculate the molar mass because we are going to need that in order to get to the moles of each of the reactants. So C2H4, we have 2 times 12.01 plus 4 times 1.008. That is going to get us 28.052. O2 is just going to be 2 times 16. And that gets 32. Remember, you do not include the coefficients when finding molar mass. And while we're at it, we might as well just calculate the molar mass of the products. So carbon, we have 12.01 plus 2 times 16. And that is going to get 44.01. H2O, we have 2 times 1.008 plus 16 equals 18.016. Okay, so now to the next part. We want to calculate the limiting reactant. So we are going to convert the mass of C2H4 into moles and the mass of O2 into moles. So we'll start with C2H4. 4.95 grams C2H4 times 1 mole over 28.052 grams. That equals 0.176 moles C2H4. Then we have oxygen, so 3.25 grams oxygen. Then we are going to divide by molar mass. And this part is just like basic stoichiometry. And then we are going to get 0.102 moles O2. And then we still have one more step to do. We need to divide by the coefficient. So C2H4 has a coefficient of 1. That equals 0.176 mole for C2H4. Now, oxygen has a coefficient of 3, so we want to divide 0.102 moles by 3, and that is going to get us 0.0339 moles O2. So now we can tell from this that the moles of oxygen are obviously less than the moles of C2H4. So oxygen is going to be our limiting reactant, and C2H4 is going to be our excess reactant. Okay, so now we know the element that we are working with. Now we need to calculate how many grams of this problem should say now how many grams of CO2 are produced. So we are going to use our moles of oxygen, which is 0.102. And remember, we are not using the number that's divided by 3. And we are going to multiply. So we're trying to get to moles of CO. We are trying to get to mass of CO2. So we are going to multiply by 2 moles CO2 over 1 mole O2. And then I'm going to put this all in one conversion fraction. We are going to write 44.01 grams over 1 mole CO2, because that is the molar mass. And if we take 0.102, multiply by 2, and then multiply by 44.01, we get 8.94 grams CO2. So I'm going to write that there, 8.94 grams. And that is our answer to this problem. Okay, so now we are going to do a stoichiometry problem that kind of encompasses everything I've explained so far, except for the one thing up here about calculating the mass of the excess reactant that is actually used and the mass remaining. Remember, you would do that by using the moles of the limiting reactant to convert all the way to mass of excess reactant that's actually used. And then if you want to get the mass remaining, you'd subtract that from your given mass of excess reactant. So here's our problem. Iron 3 iodide reacts with bromine. You're going to write a balanced chemical equation. If 218 grams of iron 3 iodide reacts with 90 grams of bromine, determine the limiting and excess reactant, determine the mass of each of the products, and if the reaction yields 115 grams of iodine, determine the percent yield And what is the mass of iron 3 bromide that would actually be produced? So give that a try on your own. Okay, so now we're going to go through the problem. Here's my balanced chemical equation. 2FeI3 plus 3Br2 yields 2FeBr3 plus 3I2. So I put in my given masses for part A over here. I converted both of them to moles, and then I divided by the coefficient, and I calculated that the limiting reactant would be Br2. And if you notice in this instance, it's really, really important to divide by the coefficient, because before you divide by the coefficient, you would think FeI3 is the limiting reactant, but it's actually not. So then I can use that for part B. And for part B, I would use the moles of bromine to calculate the mass of FeBr3 and I2 that are both theoretical masses. And remember, I am using 0.563, not 0.188. And then part C says, if the reaction yields 115 grams of iodine, determine the percent yield. So I divided 115, because that is the actual mass, by the theoretical mass, which is 143, and then multiplied by 100 to get 80.5%. And then it is asking for what mass of iron 3 bromide would actually be produced. So I'm going to multiply the theoretical mass of iron 3 bromide by the percent yield, and then I'm going to get that 89.3 grams of iron 3 bromide would actually be produced. So that encompasses pretty much all of the stoichiometry concepts I've explained. So that was this week's video. I hope you enjoyed and were able to better your knowledge of limiting and excess reactants. Next week, I'm going to start a new unit on gases, and I'm going to begin by talking about pressure. If you have any questions, feel free to leave them in the comments. And I hope you'll join me back next week if you need some extra help with talking about pressure. I hope you enjoyed, and good luck with learning the rest of your chemistry.